Hello and welcome to the Maths Jedi channel once again. This is another video in my A-level lessons series, and this follows on from quite a few videos if you've been watching my channel on the playlist A-level lessons. This is now an introduction to hypothesis testing. Particularly today we're going to talk a little bit about one-tail testing, just going through some of the fundamentals of hypothesis testing, mostly concentrating on the binomial distribution that goes well with other videos that you'll see on my channel that I've been doing in the last few days. If you're new to my channel, please do leave a like. That would be appreciated a ton. It's important to keep the support of the channel up. That would really help me out, and I appreciate everybody out there who's been supporting the channel in the last few days as we're sitting at home with all this coronavirus stuff. Right. We're going to crack on then and just have a look at hypothesis testing, just go through the fundamentals to start with, talk a little bit about some of the theory and then do a couple of questions. So let's just work our way through that. Now, first of all, with hypothesis testing, what's the point of it? So many people ask about hypothesis testing. Actually, hypothesis testing is one of the more practicable aspects of statistics. You'll see a lot of this in other subjects, particularly biology, maybe even geography, some other subjects like that, particularly psychology, sociology, those sorts of subjects, because hypothesis testing is a way of measuring how effective or how different populations of people are affected by different things. So, for example, it could be that we're testing a new cancer drug. It could be that we're testing whether speed cameras have been particularly effective. It could be that we're testing whether a candidate in an election is exaggerating the level of support, those sorts of aspects. So let's just crack on and have a look at how it's done. It's important to recognise just how hypothesis testing works. It's always very, very clear that we're working in statistics, particularly with probabilities or proportions. So throughout the whole of this topic, you'll see me working with probabilities or proportions, and that's primarily where we are. At some point, you may well study other aspects, particularly in other subjects, but within statistics, particularly the elements that go within the A-level, we're talking about probabilities and proportions, and primarily with probability, we tend to focus in on the binomial distribution. So what we're going to crack on with here is just have a look at how hypothesis testing is formed. So let's just have a look at a little sort of simple introductory example. It might be that you're looking at a particular die, a die that's biased towards the number 6. You're not sure, but you suspect. So you throw it through times, and you throw it 20 times in this example, and you're seeing how many times that you get a 6. Of course, if the dice was fair, you'd expect it about 1/6 of the time, so about 4 times possibly. That would be a sort of normal standard amount of times that you would expect to see a dice. But at what point will you decide that the dice is fair? And at what point will you decide that the dice is biased? Because of course, the amount of times that you repeat that experiment, you will get different outcomes. And it's important to recognize when those outcomes are what we call statistically significant. So what you have to do is gather evidence and understand how to be statistically significant, the point at which you decide on what a suspicious number of 6s happens to be. Now this tends to be referred to as a critical value, and we'll talk a little bit more about critical values as we crack on through this presentation. So when we're doing hypothesis testing, we're primarily essentially presented with two particular pathways that we might follow. One of those pathways might be that a coin is fair or a coin is biased. It might be that a proportion of local people is smaller or equal to. It might be that you have a drug having effectiveness that's the same or more effective. And these different rival hypotheses are referred to as the null hypothesis and the alternative hypothesis. So it tends to be the null hypothesis is the one which is fairly cautious, the one which we expect to be true, and the alternative hypothesis tends to be one we're trying to prove something. It might be we're trying to prove that proportions are different, more, probabilities are higher, that sort of thing. So it tends to be the null hypothesis is the cautious one, and the alternative hypothesis is where we're trying to prove something particularly. This is just emphasizing that point. So as I mentioned, just representing the usual state of affairs as the null hypothesis, the neutral hypothesis, and until the alternative hypothesis, which we usually refer to as H1, H0 is usually the null hypothesis. It's usually one where we suspect or hope to be true. Now, importantly, we want to mention about significance level, because statisticians are never 100% sure that they're proving or disproving something. We can only be statistically or not statistically significant. The significance level of the test is the chosen cutoff value, as you can see here. That's where the critical value that I referred to earlier occurs. And it tends to be, we're working with probabilities probably around 10%, 5%, 1%, sometimes very rarely at 0.1%. Most of the time with A-level questions, you tend to deal with 10% or 5%. It's always stated in the question. The important note here is emphasising the point I was just making, that we can never be definitely true in statistics. We're only ever giving as a degree of significance, measuring things in terms of risk. That's all we can do. So we're going to first of all talk about one-sided hypothesis testing. We are going to talk about two-sided testing in the next video, so be aware of that. We're going to focus in on one-sided testing for today, and all the examples you'll see will be one-sided hypothesis testing that we'll focus on. So here's a typical question that you might get. We're going to look at it in detail, really understand it, and we're going to do a couple of examples from the book also. So this particular question talks about a candidate in a local election. He claims to have the support of 40% of the electorate. He has a rival candidate who believes that he's exaggerating his level of support. She's asking for a random sample of 12 local people, and she discovers that 3 of them support Mr. Jones. And she wants to understand if that's a 5% significance level to see whether Mr. Jones is exaggerating or whether he's not. So in this example, to start off with, we talk about the significance test. So what is the significance test here? Well, the two hypotheses first of all. H0 is the null hypothesis. That's where we're assuming the probability of those that support Mr. Jones is 0.4. Remember, he said 40% of the electorate support him. The alternative provision here is when we're doing P less than 0.4. She believes that the probability of those that are less than 40% support him. So she wants to prove, or she wants to try and prove that less than 40% support him. So that's the alternative hypothesis that we're trying to deal with here. We always write them mathematically. We always try and write them in terms of probability or proportions. The significance level we were asked for was 5%. We're going to talk about X, first of all, as being the number of people in the sample who support Mr. Jones. So if we are talking about X, how does X generate a distribution? Well, going back to previous videos, we've got a proportion which is fixed, it doesn't change. Hopefully one person's opinion doesn't affect another person's opinion, so you've got independence, you've got a fixed number of trials, hopefully. So in this example, a binomial distribution seems to be the best way. And it will be the binomial distribution that will be of size order 12, because the sample she picked was 12, and the proportion 0.4, probability 0.4 of success. We're looking at the observed data, and she said that 3 out of the 12 were saying that they supported him. She wants to see if the result is so extreme that that must mean that less than 40% support him. So in the probabilities here, what we're looking at is the observed data 3 out of 12. Now, because she's assuming, or she wants to prove, that less than 40% of the population support this guy, she's looking for the probability of at most 3, at most 3. So what we're going to have to do is calculate the probability of at most 3. We can do that from tables or with a calculator. In this example, they work it out by hand, so you can see them working out by hand here. So this is at most 3. All the probabilities of 3, 2 and 1 and 0 added up, the cumulative probability. And they're getting 0.225. Now, what does that value actually mean? Well, 0.225 is obviously 22.5%. It's more than 5%. The fact that there's 3 people in 12 is not statistically significant. It's not less than 5%. And so in this example, H0 can't be rejected. She has to assume that he is not exaggerating his support. So the steps in a hypothesis testing, let's just run those through, make sure you've got them understood, because we're going to follow them in a minute. Step 1, write out H0 and H1. Always write them in mathematical terms with a proportion or a probability. We're going to state the significance level if none is mentioned in the question. It's usual to choose 5%. We're going to state the distribution, assuming the null hypothesis to be true. For most questions that you'll do, the distribution will be binomial. We're going to calculate the probability under H0 of obtaining results as extreme as those collected in your particular sample. And we're going to see if those values are in the critical region or not, if they're higher than a particular critical value. So time to do some questions now. We're going to crack on into the book. We're going to finish this presentation for the moment. We're going to look at the book. So here in the book, I've picked out a particular question. Just to start with, just to introduce you to the concept of statistical testing, get you to grips with what's going on. This is on page 101, and this is question number 5. So we're going to start off with this question just to show you the kind of thing that you might be asked. This isn't a typical exam question, but just gives you a feel for some of the things that you might be expecting to get. So it says here, in a manufacturing process, the proportion of faulty articles has been found from long experience to be 0.1. A sample of 100 articles from a new manufacturing process is tested and 8 are found to be faulty. So there's a couple of things I'd mention here. First of all, the sample being 100 size. First of all, that there's 8 articles found that are faulty. Those are things that are worth mentioning. The manufacturers wish to test at the 5% level of significance whether or not there's been a reduction in the proportion of faulty articles. So one-tailed test, because we're looking for a reduction. We'll talk a little bit more about two-tailed tests next video. It says suggest a suitable test statistic. So what is the test statistic here? Well, the test statistic will be those articles that are faulty in the sample of 100. So we can start off by stating that, making sure that we've got a good understanding about how those things are set. So we're going to just set this to pen, and I'll write this down for you. So we're going to state the X statistic as being the number of articles that are faulty in the 100, in the sample of 100. So I have to write quite slow with this pen. So the number of articles that are faulty. You have to mention the sample size because it's important that you do that. And that would be the answer to part A. Then it says write down two suitable hypotheses. Well, these hypotheses, the null hypothesis first of all, and then the alternative hypothesis. So what does that null hypothesis say? Well, the null hypothesis will be saying that for your particular sample, you've got a manufacturing process that has 40 articles, probability of being 0.1. So that will be what the proportion will be, or the probability will be here, 0.1. And then they're trying to test if he has been reducing that proportion. So the alternative hypothesis here will be that it is less than 0.1. Then it says, explain the condition under which the null hypothesis is rejected. Well, we would need to look up in the probability situation here whether the probability of it being less than or equal to 8 in other words, at most 8, is going to be less than 5%. Why is it 5%? Because we're testing at a 5% level of significance. If this was true, then H0 would be rejected. So probability of less than or equal to 8 is less than 5%, H0 would be rejected. That's the conditions under which the null hypothesis is rejected. I want to spend a little bit of time just before I move on, just talking about what kind of distribution this would be. So just go back to my previous videos, you'll see what I'm referring to here, but these conditions always seem to come up time and time again, so I'll quote them again. We have a fixed probability, 0.1, it won't change. Hopefully the articles will be, the 40 articles will be independent of each other, so one 40 article doesn't create another 40 article. It will be a fixed number of trials because I've got 100 articles, and the probabilities won't change. So hopefully in this example we do have a situation which is going to be equivalent to a binomial distribution, and that binomial distribution will be size 100, and the probability that we want for 6/4, in this case if we call it success, even though it's 40 articles, we say it's going to be 0.1. And so that would be the table that you would look up, or the calculation that you would use to test this last statistic if you were asked to. So now we need to get into some more detailed examples. Let's look a little bit further on into the book. We're going to look now at example or exercise 7b. So I'm going to scroll down and just find myself into exercise 7b. And we're going to particularly focus on question 7. So in a moment you'll see that coming up, and I'll try and highlight that for you as I go along. So we're going to look at question 7 here. Number 7, first of all, talks about a mechanical component failing on average 3 times out of every 10. An engineer designs a new system of manufacture that he believes reduces the likelihood of failure. He tests a sample of 20, and then we're asked to describe the test statistics. So like in the previous question, what's a test statistic? So the test statistic will here be, it will be the number of items that were failing in the sample. I'm going to try and write that. It's hard to write with this pen. So number of failed items in the sample, that's going to be the test statistic. The null and alternatives, so we're going to state H0 and H1. So what's the null hypothesis? Well, the null hypothesis here, the proportion isn't changed from 3 out of 10, so that's a probability of being 0.3. And then he's hoping he's got a new system which is reducing the likelihood of failure, so we're going to have P being less than 0.3. That's the alternative hypothesis. And then we're going to look at a critical region, see what's going on. So let's have a look at this, first of all, this particular example, and see if we can come up with the distribution that follows it. Again, as with the previous example, it's a fixed probability. It doesn't change. The events are independent. There's a fixed number of trials, 20 trials in this case, so it will follow a binomial distribution. So you can see how that might come together. So we're going to just write that in there. So we're telling the examiner that I know it's a binomial distribution. Size 20, probability 0.3. And then we're looking at a 5% level of significance. And it's asking me to find the critical region for a test to check its belief. And we want it as close as possible to 0.05. So we need to look at a few probabilities here and understand what's going on. So first of all, 20 and 0.3. Now it'd be handy to use the tables or use the calculator for this. Tables probably for this one is slightly better, so I'm going to use the tables for this one. So this again is the set of tables that are available in the exam. We're going to just have a look at this table in just a sec, but I'm just going to clean up the screen so you can see it a bit better. So clean those things up. And then we're going to look at the table. So first of all, we've got 0.3. That's because this is 0.3. And then we want the size to be 20. So you can see that down here, size 20. So it's this column we're looking at. We're looking for probabilities to be less than 5%. So we're particularly concentrating on this probability here. You can probably see it here. These two particularly, I suppose, would be the two to look at. We've got 0.1071, that's 10%. And we've got 0.0355. So that's the one, this one here, that's less than 5%. That corresponds to 2. And so it is 2, probability of it being less than 2 that we need. So the critical value will be anything less than or equal to 2. Of course, because it's less than 5%, we have a real probability here. It's not going to be 5% that our significance level is going to be. It's actually going to be 3.55%. To emphasize that point, the question does ask that, so I want just to delete this off and I'll show you that real quick. So here's back to the question, and you can see here, find the critical region for a test. This is the critical region, anything less than or equal to 2. And then it says write down the actual significance level of the test. This is the actual significance level because it was 3.55%. So that goes through a question from start to finish there, just relatively straightforward once you get used to it, what's going on. Some of the questions in this particular exercise are two-tailed testing, so you might want to watch the next video before you attempt some of them, but some of them are one-tailed testing, and I would encourage you to try some of the others. We're going to do number 8 real quick, just to emphasize the point, just to get a bit more practice. So I'm going to clear my annotations and look at number 8. So number 8 says about seedlings coming in trays of 36. On average, 12 seedlings survive to be planted on. A gardener decides to use a new fertilizer on the seedlings. She believes it will improve the number that survive Okay, so we need to see, first of all, the test statistic. I'm not going to write it down this time, but I'm going to talk to it for you. So the test statistic will be the number of seedlings that survive in the sample, number of seedlings that survive in the sample. And we're going to state the null and alternative hypothesis. So we'll write those down. So H0 and H1. So H0, first of all, will be that we've got 12 seedlings surviving out of 36. So that's a third. And she's hoping to have improved that, so that's going to be P is more than a third. And then we're looking at whether it says using a 10% level of significance, that's 10% this time, find the critical region for a test to check her belief. Now, this is where having a calculator is really handy, because we're establishing in a minute how to use the calculator, the binomial cumulative distribution function on the calculator to help me do this. I would definitely encourage you to look at my previous video, which goes through that in detail. We are going to do it a little bit today, but not as in much detail as the previous video. So if you're getting a bit stuck on what I'm about to do have a look at the previous video. It's important just to go through and understand what's happening with that. First of all, to establish what kind of distribution we're looking at, again, we're asking for a sample of size 36. The probability stays fixed. Whether one seedling survives is independent of another seedling. So here it's, again, a classic situation of a binomial distribution. Size 36, probability of a third. I'm going to pull my calculator up now so I can show you what I'm going to do with it. Let's move it to one side slightly. Here we go. Okay, so just like last time, the last video, we're going to look at a little bit here. We're going to look at a different mode, different sort of part of the modes. So we're going to look at mode, first of all. We're going to look at mode 7. So the previous video went through this in detail. We're going to look at binomial CD. But this time for this question, I'm going to use list. I did describe how to use that in the previous video, but I'm going to use list here just because it helps me to do some of the things that I want to do here. So what it's asking for is the critical region. We don't know where that critical region is. We're looking for a number above 12, but we don't know where it's going to be. So what I'm going to do here is I'm going to look at 13, 14, and keep putting numbers in for a little while just to test out different values, just to see where I get into that critical region. I'm going to try and cover as many numbers as I can. I'm not sure how far the calculator will allow me to go. I think that's probably enough. I'll do one more. Okay, so now we're going to put in a binomial distribution, 36. And then a third. So you can use the fraction button still. It will convert it for you. And then if you can see that, we're going to look at these values in here to get to grips with what's happening. So we're really going to concentrate on these values and seeing where we're getting into this 10% level of significance. Now, to be a 10% level of significance, I'm looking for a probability that's more than 90. I'll explain a little bit more about why in a minute. But let's have a look at these values and see if I can get a probability that's more than 90. So if you look on the calculator here, you can see these two values, 15 and 16. I'm just going to sketch them down here at the side so you can see me writing them down. So the probability of less than or equal to 15 is 0.8905. Okay, if you wanted to see what that value was, you could actually use the calculator to get that for you. So 8905657888. You can copy the whole thing to avoid rounding error. But for the moment, I'm not too worried. And the probability is 16, the next one down. That's less than or equal to 16, of course. Is 0.9416. Okay. Let's clear the calculator off because I won't need it anymore now. But I'm going to explain what's going on here. So these two probabilities are around the 90% mark. That's important for me. Remember, we're looking at it being more than a third. So she has to have it more than a number, more than 12, significantly more than 12. So if we're looking at the probability of it being more than or equal to 16. How would I work that out? Well, I'd work that out by doing 1 minus the probability of it being less than or equal to 15. And if I was looking at the probability of it being more than or equal to 17, I would do 1 minus the probability of it being less than or equal to 16. Now you can see the values up here. Only one of those values is going to produce something that's less than 10%. So 1 minus this will produce less than 10%. 1 minus this will produce more than 10%. So it's not this one that I need, it's this one. 17 is my critical value. So 17 or more will be where we start to understand that H0 can be rejected. So it's going to be talking about the critical region for a test to check a belief. It's the region that's more than 17 that I need. If I pull the calculator back up again, we're just going to go into calculate mode. And I'm going to do 1 minus my 0.9416. And that's 0.0584. So actually, it's far less than 10% significance here. The probability of incorrectly rejecting H0 using this critical region is 5.84%. And that's what's covered in part C. So state probability of incorrectly rejecting H0 using this critical region, because I'm getting a statistic that's far less than 10%, it's 5.84% is the chance of rejecting it. She has to have 17 or more. Okay, we're going to do one more exercise, and that's exercise 7C. This particular exercise is concentrating primarily on one-tail testing, so you can do the vast majority of this exercise after this video is over, and I would definitely encourage you to do so. We're going to focus in on question number 8, and we're going to do one more as well, question number 9, just to give you a feel for this thing, so you can see what's happening, and we're really going to sort of really focus in on different aspects of those particular questions. So question 8 first of all talks about the success rate of a standard treatment. It's talking about 68% and a sample of n patients. X is the number for which the treatment is successful. Write down a suitable distribution to model X and give reasons for your choice of model. Well, again, it's another classic test of those conditions that I've been talking about for about 3 videos now. So let's just focus in on that. Fixed probability, 68%. Independent events, one patient's suffering is hopefully not going to affect another patient's suffering. Fixed number of trials, however many patients it is. The probability won't change, hopefully, so it is a binomial distribution. It will be a binomial distribution of size n, probability of 0.68. You would need to give reasons, and those reasons are the reasons I've said, so you just need to go through that. For part B, it says a random sample of 10, so we're now modelling a distribution of size 10. And it says, in only 3 cases was the treatment successful. It is thought that the standard treatment was not as effective as it's claimed. So, a good H0 coming up here, and a good H1 coming up here. H0, the null hypothesis, probability isn't changed. H1 is the alternative hypothesis, and if we're saying that the medicine is not as effective, it means the proportion of those that are cured is going to be less than 0.68. So if you read that carefully, it's saying the success rate is 68. We're trying to show that it's not as effective, so it's less than 68%. We're testing the claim at 5% significance level, so now we need to look at the 5% significance level. So again, we're looking through our standard data here. Particularly, we're looking at the number of patients in the sample. So only 3 cases in a sample. So we're looking at 3 cases out of 10. So we're looking at the probability of it being less than or equal to 3. What that will be. So I'm going to pull up my calculator once again. This won't be available in the tables because it's an unusual binomial distribution. We're going to go through and do binomial CD mode. This time I'm going to do variable, and we're going to go through and put the variables in. So 3 in this case, and then 10, and then 0.68. Calculate that through. We get 0.0155. So what's the significance of 0.0155? Well, 0.0155 is 1.55%. That's significantly less than 5%. So actually this is in the tail of data that we need. So actually this is in the critical region. It's going to be less than 5% here. So the fact that it's less than 5% means that H0 is rejected and H1 is accepted. It must be that this particular treatment is not as successful as the medical company claims. Just to double check the answers. And you can see it here. They're looking at less than or equal to 3, 0.0155. They're saying it's less than 0.05. There's sufficient evidence to reject H0. So the treatment not as effective as claimed. You can see that there. Let's clear my annotations. Let's crack on into number 9. So a plant germination method is successful on average 4 times out of every 10. A horticulturalist develops a new technique which she believes will improve the number of plants that successfully germinate. She takes a random sample of 20 seeds and attempts to germinate them. Using a 5% level of significance, find the critical region for a test to check her belief. So again, as with earlier examples, we need to state the binomial distribution. So it's a binomial distribution this time, size 20, probability of 0.4. And we're looking at the two hypotheses, H0 and H1. H0 will be probability is unchanged, 0.4. Probability of H1 will be the probability is more than 0.4. She's thinking that her method is more successful. And then again, we're going to pull up the calculator to look at how significant these things are. Again, we're going to use our friend mode 7, binomial CD. We're going to use the list mode again. We're going to look at critical values. But what critical values am I going to put in? Well, the clue is in the question. Let's just go back to the question. I'd like to pull it down so you can see what values we're going to use. So she's taking a random sample of 20 seeds. So that's important, and she's getting a plant germination method that's an average 4 times out of every 10. So we're trying to make it more successful than 4 times out of every 10. So in a sample of 20, maybe 8 or so would be the normal. So how far beyond 8 do we need to be successful? That's what we're going to test here. So we're going to put in a few values here and have a look. So 10, say, 11, 12, 13. We're going to put those values in. Binomial distribution with n20, probability of 0.4. And you can see that I've got all the different probabilities put down there. Because we're looking for a 5% significance level, I'm particularly interested in the ones where I'm getting it being more than 95%. So you can have a look at these values and just take a look with me. So you can see these two here are around the 95% mark. So I'm particularly interested in those. So probability of it being less than or equal to 11 is 0.9434. And probability of it being less than or equal to 12 is 0.9789. Move the calculator to one side. Again, as with the previous question we did a little bit earlier, these are significant because they're around the 95% mark. Just like earlier, we're looking for the value where she's more than a certain amount. So if you think back to what I did earlier, if we're looking for more than or equal to 12, that would be 1 minus the probability of it being less than or equal to 11. And you can see that probability would be more than 5. But this one will be less than 5%. Probability of it being more than 13 will be less than 5%. So it's actually going to be this one is the critical value, 13. So I'll clear my annotations and make a note of that. So probability of it being more than or equal to 13 will be where you get the critical region. This is tested in part B because it says of her sample of 20 plants, The horticulturist finds that 14 have germinated. Comment on this observation in light of the critical region. Well, because 14 lies in this zone, it must be that H0 will be rejected. So H0 is rejected for part C. Excuse the writing. And so I'm going to put up the answers just to have a look at that. So let's just clean them up so you can see what's going on. And here we have that being followed through. So you can see the probability distribution here is 20, p. We had 0.4, more than 0.4. They were looking at the same probabilities as I was, so 12 and 13. They can see one is less than 5%, one is more than 5%. And so they're looking for whether one is less than 5%, the critical region being more than 13. And hopefully over the page you can see, because 14 is lying within the critical region, we can reject the null hypothesis. So those are just some of the basic questions we can see here. We've done quite a few there, for 4 or 5 questions that we went through. I would encourage you to try the remainder of exercise 7C, because all of those are one-tail tests, and you can definitely work your way through the method and understand it a bit better. I would wait on exercise 7P and 7B until you've seen the next video, which is on two-tail testing, because some of them are on two-tail tests. And at that point, hopefully you'll be confident enough to go back and try some of exercise 7B also. In terms of today's video, that's enough for today. I would appreciate it if you could leave me a like or subscribe. That would help me out a ton. And I do wish you a very good rest of the week. Bye.